Hello everyone. First of all, I would like to thank the organizers for having me here today, giving me the opportunity to talk about a decade of SQM light pollution measurements in Austria. This is a large project where many people are involved. However, from the scientific point of view, it is mainly Stefan Wallner, who you see on the right, and me. The outline of the talk is as follows. I will start giving you some insights into the early days when we installed the first SQMs and show our first results. Then I will show how with time we established a network of SQMs that we are still operating in Austria and also at some other sites. In the third part of the talk, I will then talk about long-term trend analysis and how we recently published it. And then finally, I will conclude with some remarks after 10 years of involvement. This is me standing in front of a small radio telescope at the University Observatory in Vienna. The site is roughly 3.5 kilometers from the city center. You can see here that we have installed in these early days 2 devices in parallel. We did this in order to test the reproducibility of the results. So finally, we could conclude that the SQM is of use for scientific studies because the uncertainties are as low as 0.04 magnitudes per square arc second. And also for this particular case, we found a calibration error of only 0.04 magnitudes per square arc second, which is better than the limits provided by the manufacturer. However, we also found some problems. So in this case, you see 4 scotographs or light curves gained during 4 nights. In red, you see the measurements of the night sky brightness obtained by one of the devices, and in blue, you see the difference between the 2 devices. So the blue curve should always be a line around 0, but it's not. In particular, we found that when the moon is at a certain azimuth angle, then these problems occur, and we find discrepancies up to 0.6 or even 0.8 magnitudes per square arc second. So we concluded from this that it must be scattered moonlight entering the system, leading then to spurious results. However, there was a very simple solution to this. You just need some kind of shielding on top of the device, as you can see here in the image on the right. And this then solved the problem. One of the main early results is the impact of clouds on the night sky brightness. Here you see a density plot, which is sometimes also nowadays called jellyfish plot. So we see here the number density of measurements in the time versus night sky brightness plane. Clearly, we can identify 2 islands where most of the measurements fall. The bottom island here is when the sky is clear. The top one is when it's overcast or cloudy. So clouds have a strong amplification on light pollution. This was one of the main early results. Furthermore, we obtained a night sky spectrum of the Viennese night sky that you can see here, and we decomposed it into 2 main components, namely high pressure sodium lamps and fluorescent lamps. Also in this early paper, we stated that currently the blue end of the spectrum below 525 nanometer does not show any significant contribution to the night sky brightness. Now, shortly after the success with the first SQMs, we started a cooperation with the local government in Upper Austria, who agreed to establish a network in Upper Austria of several tens of devices, and by January 2016 we had then a total of 28 SQMs in operation. The big advantage of the Upper Austrian SQMs is that they are situated at sites where also meteorological parameters are measured at the same time, and this led to one of the very nice results that we show here, published by Posch et al. 2018, where we can see a clear trend between the SQM brightness as measured by the SQM on the x-axis versus the particulate matter on the y-axis. So the more particulate matter, the brighter it gets due to scattering of light on these particles. Another surprising result that is also shown in this paper is when we do a difference of these density plots obtained in 2017 and 2012, we see that the newer measurements, they fall into a region of darker measurements, meaning that we would see a darkening of 1.8% after 5 years of measurements in Vienna. We doubted this from the beginning, and since rumor was already around that there may be some kind of aging effect going on with the SQM, we speculated that what we see here is actually the change of transmission of the housing window of the SQM. So back in 2018, we revealed several challenges. First of all, the aging effect, which was unclear how strongly measurements are affected by change of transmission with time. Then we didn't tackle any meteorological conditions yet. So in principle, one would also want to correct for changing atmospheric conditions. And then the third obstacle is the change of the underlying night sky spectrum, which is important doing long-term trend analysis. There was a publication that I'm referring to here also by Sanchez de Miguel et al. 2017, showing that a site that undergoes a change from mainly high pressure sodium to LEDs of 4000 Kelvin. In this particular case, the SQM would just detect an increase of 0.24 magnitudes, whereas the scotopic human vision would perceive the same change as an increase by a magnitude. So why is this? This is because the sensitivity curve of the SQM that you see here on the top does not match the sensitivity curve of the rods. In particular, the SQM sensitivity seems to be asymmetric, in particular showing less sensitivity in the blue compared to the right end. So any change towards bluer skies may only be recognized by the SQM as a lower limit, so to speak. We were able to solve for the aging effect by using the twilight as a calibration source. The basic principle behind this is that based on the sun altitude, we can model the night sky brightness and then compare our observations to these models and follow this up over time. Here's just a qualitative way that shows how the sensitivity of the SQM must have changed with time. In the top panel, you see a zoom in of the measurements of the SQM measurements during twilight in gray, whereas our model predictions are shown in green. And then you can see that 8 years later in the bottom, the SQM measurements tend to give darker readings than 8 years before. So this is just qualitatively showing this aging. When we do then this evaluation over the course of time, we can get here a kind of linear trend. For the example, here in Berlin, we see a darkening of 0.046 magnitudes per square arc seconds. All the details are published in Buschnick et al. 2021. In order to quantify the impact of the atmosphere on SQM measurements, we make use of Copernicus satellite data that are freely available, and we will feed those to our empirical atmospheric model, which is a very simple model, in fact. And how the model looks like, you can see here in the bottom formula. Y dash is basically the predicted night sky brightness based on the change of atmospheric parameter Xij. The list of these atmospheric parameters is shown here in the right. I will go through it in a minute. And then what we do is to make regression, a linear regression between the observations and the models to determine the best fit parameter. And then this will allow us to study the importance of individual atmospheric parameters for the night sky brightness or for the changing night sky brightness. So overall, this is a multivariable penalized linear regression only. And the parameters that we are considering are albedo, the leaf area index, which is a number that represents the state of vegetation. We consider several aerosol optical depths, like those of black carbon, dust, sea salt, or organic matter. Then we have particulate matter concentrations in different grain sizes. We have total column water vapor, total column ozone, the cloud cover, and snow depth. So these are the parameters that we selected as potentially important for changing the night sky brightness. What we see here is now our SQM data versus the models as well as the residual. So we do this for two sites, Potsdam in the left and Bodingraben to the right. Let's start with the right figure. In the top panel, we see our observed aging-corrected SQM data under clear and moonless conditions over the course of several years. So we can clearly identify a very strong seasonal pattern. Now, when we use the atmospheric parameters, as I listed them before, we can just by using the change of these atmospheric parameters, we can already very well reproduce the seasonal variations. And this is seen best when you look at the residual in the bottom right. Finally, the distribution is really a nice Gaussian scatter. So the models help us with two things. First of all, when doing just a linear fit through the data, due to the large seasonal variation, one may introduce some kind of bias depending just on the distribution of the data points along the seasonal variations. So the models help in removing this kind of observational bias and determine the true underlying linear trend in light pollution. And second, the models also help in studying the importance of individual atmospheric parameters for the night sky brightness. So as we have seen here at the rural site, all this works very well. In the urban site here in Potsdam, it seems that the models don't do such a good job. This is, we think, mainly because our aerosol optical depths have a very coarse spatial resolution of only 80 kilometers. So this is not good enough to represent the actual conditions. So this is the models here fail because of the poor quality of the data, most likely. I will skip this slide and show you here how we actually are now able to infer the importance of individual parameters for the setting of the night sky brightness. So to the very left, we see when we just have a linear model and we fit a linear model to the data, how good is DMA rank correlation? It's very poor, it's only 0.24. When we then increase the complexity of our models by adding different parameters, so by adding just albedo as a parameter, we already reduced the scatter by a lot and also the correlation and so on. And finally, when we consider all these parameters, we end up very, very high correlation of 0.70 almost for our rural sites. So the thick line here is just the mean overall, the mean trend over all sources. And clearly we can see here that on average, albedo and the state of vegetation play the most important role in setting the seasonal variation. But for some sites, for example, we have here Bodingraben, we also see that organic matter aerosol optical depths makes a difference. And at some sites, such as Gisela-Warte, I think we also see that snow depth plays an important role. Now we come to the impact of temporal changes of the night sky spectral composition. I've already mentioned this earlier, that the SQM in particular, when we have a shift towards bluer skies, is only able to give some kind of lower limit on the temporal trend. So for one of our sites here in Vienna, we have actually obtained spectra in 2022 and 10 years earlier in 2012. I've shown this before. And as one might have expected, what we see now compared to 10 years earlier is that the flux in the blue is getting much, much stronger. Here, when we compare, for example, the flux at 520 and 650 nanometers, we see now that at 520 nanometers, the flux has increased by a factor of 4 compared to 10 years earlier. So this is something we still want to fold into our previously published results of Pushnik et al. 2023. Now I conclude my talk. I think photometric measurements with the SQM are still a robust and easy way to continuously monitor the genital night sky brightness. However, I want to point out that single band photometry may be problematic due to changing spectral composition of the night sky, and filters should be used when using SQMs, for example. Finally, as time is running, I just want to make a final statement. that it's really a pity that we haven't achieved the goal that night sky brightness is considered as a very important environmental parameter that is also measured by meteorological station organized by governments or other local authorities. Thank you for listening.